Okay, so this is more of like a little discussion on classifying discontinuities. I'm going to go through it pretty quickly, and we're just going to look at these two examples and then flip to the back side. So while limits told us where a function intended to go, continuity guarantees that the function actually made it there. So there's two different types of discontinuity. One is removable and one is non-removable. So this one is wholes and two-sided limits. And this one is jump and infinite. So we're going to talk about these two examples down here. Discuss the continuity of the following. This one is a non-removable. Oh, let me turn my lights back on. So the first one we're talking about is a non-removable discontinuity because it is a step function. And because it has infinite discontinuities. At integral, I can't spell, x values. So there's discontinuities like throughout it continuously. And it's not just a point, there's continuous jumps basically being made. So this one is also a jump, which means that it's non-removable. And this is mostly like what a piecewise function is going to look like. And because of that, for x is less than 3, the limits as x approaches 3 from the left is equal to -1. And then for x is greater than 3, the limit as x approaches 3 from the right is equal to +1. So because these aren't the same, which we've talked about in our notes already, there is a discontinuity. All right. Last thing we're going to talk about for this activity are talking about whether or not these are continuous or not and defending our answer with a condition from the 3-point definition of continuity. That is f of c, the limit of f of c, does it exist as x approaches from the left and from the right? And we're going to work those examples. And again, I'll work the first one. Feel free to pause once you kind of understand what we're doing and try to work one or two on your own. So first one is definitely not continuous. So I'm just going to put a big no there. There is a jump. Again, this is what a piecewise kind of looks like. We come up to 1 and then jump up here and go down. So first things first, f of 1 is equal to 3. Okay, and then we have the limit of f of x as x approaches 1 from the left, which is going to be 1, and the limit of f of x as x approaches 1 from the right is 3. So because of that, the limit of f of x as x approaches 1 in general does not exist because these two are not the same. Okay, on to the next one. Is this one continuous? No, there is a point missing. And so because of that, first things first, f of 1 does not exist. Number 2, the limit of f of x as x approaches 1 from the left is 2. And the limit of f of x as x approaches 1 from the right is also 2. So the limit of f of x as x approaches 1 exists. However, f of 1 is a point that does not exist. So that still means that there is a discontinuity. And our final one is continuous. Yes, there's nothing missing. And just to kind of show, f of 1 is 2. The limit of f of x as x approaches 2 from the left is 2. And the limit of f of x as x approaches 2 from the right is also 2. And therefore, the limit of f of x as x approaches 2 is 2. Oop, I'm sorry. This is supposed to be 1, not 2. 1, 2. And then as x approaches 1. My bad. Too many 2's. Got a little lost there. All right. Without graphing, justify why the functions are continuous for all real numbers. So, I mean, obviously, when you're working on your own assignments, you can graph. I highly recommend graphing because it's always good to check your work. But these are just kind of ways that you can know whether or not it's continuous. So, these are all continuous. We're going to talk about why. Exponential graphs, for one, are all continuous for all real numbers. All right, talking about this one, we have a cube root here and we have a squared function. So because of that, it's the nth root is odd. So because it's a cube root or a fifth root or a seventh root, when that root is odd, y is continuous at all real numbers. Because if you think about it this way, if our x value is negative, even if this square wasn't here, if our x value is negative and we're taking a cube root, you can cube root a negative number. If it were square root of a negative number, we couldn't do that. But because it's a cube root, it's an odd root, we can still use negative values for x. Okay, so that's kind of why that works. All right, 2x minus cosine. This is a linear function. And its cosine. Both of these are continuous functions. So they're both continuous on their own, and that's why they're able to be even meshed together. They're still going to be continuous. All right, and then we have g of x is equal to 1 over x squared plus 1. So since x squared plus 1 cannot equal 0, there's no way that can equal 0, because the only way we would have an asymptote is because x squared plus 1 is equal to 0, right? That's about the denominator here. There is no vertical asymptote shown by looking at it, right? And you can graph it as well. But because of that, x squared is equal to negative 1. We can't square root a negative number. Therefore, there is no horizontal asymptote either. That means g of x is continuous. There's no asymptotes anywhere. No slant, no horizontal, no vertical asymptotes. It's going to be continuous. All right, and that is all of our continuity activity.